Continuing on with the organic chemistry lecture series, we're going to be discussing Chem 112, Chapter 4, which focuses on alkanes, cycloalkanes, and talking a little bit about chair conformations, as well as discussing Newman projections and other methods of conformational analysis for cyclic systems. So let's talk a little bit about cycloalkanes. So as we discussed previously, alkanes are hydrocarbons containing only carbon and hydrogen atoms connected by single bonds, no pi bonds. The formula for a straight chain alkane is CnH2n plus 2, where n is the number of carbons. Cycloalkanes are named with the cyclo prefix, and to name a cycloalkane, you add the cyclo prefix to the name. As the name implies, cycloalkanes have the carbons arranged in a ring. So for example, cyclopropane would be a 3-carbon ring, cyclobutane, 4 carbons, cyclopentane, 5 carbons. How would we name a 6-carbon ring? In this case, we'd add the cyclo prefix. This would be cyclo, 6 carbons is hexane. In terms of naming substituted cycloalkanes, cycloalkanes are named with the cyclo prefix. When you're numbering cycloalkanes, you number the carbons counting around the ring either clockwise or counterclockwise. You're going to use the set of locant numbers with the smallest first locant number, and if there's a tie, you'll compare the next or the second locant number. So for example, this following compound would be named as 1-ethyl 3-methyl cyclopentane rather than 1-ethyl 4-methyl cyclopentane or 1-methyl 3-ethyl. To talk about why that is, first and foremost, 1 and 3 are the lowest possible locant numbers. In the event of a tie, E is first alphabetically, so the ethyl group gets the locant number of 1 in the event of a tie. Let's take a look at this next example. So in this case, we have a 6-carbon ring. So this is cyclohexane. I'm going to start numbering to try to get the lowest locant numbers on the most substituents. So starting with this methyl, I can number 1, 2, 3, 4, 5, 6. Or I can count from the other methyl, 1, 2, 3, 4, 5, 6. In this case, the locant number set of 1, 2, 4 is lower than the other possible locant number set of 1, 2, 5. So we'll name this as 1, 2, 4 trimethyl because we have 3 methyl groups, cyclohexane. Let's now work on some additional examples. So let's try to name the following compounds. You may want to pause the video at this time and work on naming the following compounds. One thing I'd like you to remember is the iso prefix is included in alphabetical order. It's one of the few prefixes that we do have to account for in terms of alphabetical ordering. And you'll see why that's important momentarily. So take a few moments to work on these examples, and then we'll discuss. Okay, so in this case, we're going to set up our locant numbers to place the lowest locant numbers on the greatest number of substituents. If you have substituents next to one another, you generally want to start numbering in that group of substituents. So I'm going to number counterclockwise. So 1, 2, 3, 4, 5, 6, 7. Let's look at another possibility where we number counterclockwise. For those wondering, why didn't I entertain counting at the ethyl group going clockwise? That would give a set of locant numbers, I'll show that, of 1, 2, 3, 4, 5. 1, 5 is much less preferred compared to 1, 2 in terms of locant number ordering. So we really have two choices. In this case, let's list our locant numbers. So in this case, we have 1-ethyl, 2-methyl, 4-methyl, versus the alternative set of locate numbers, which have 1 methyl, 2 ethyl, 6 methyl. In this case, the tie is broken at the third locate number, and we're going to use the smallest set of locate numbers sequentially. So we'll use the locate number set 1, 2, 4. So we'll name this as 1 ethyl. E is first alphabetically, so it goes first in the name, regardless of locate number. Next, we name this as 2,4 dimethyl. Remember, the di prefix is not included in alphabetization if we have multiples of the same substituent. Finally, this is a 7-carbon ring, so this would be cycloheptane. Looking at this next example, this group here is an isopropyl group. Looking at our locate numbers, we can do 1, 2, 3, 4, 5, or we can count the other way, 1, 2, 3, 4, 5. In this case, we can either have locate numbers for 1 isopropyl, 2 methyl, 4 ethyl, or 1 methyl, 2 isopropyl, 4 ethyl. In this case, we have a tie in locate numbers, so we look at alphabetical order. Iso, this is one of the few prefixes that is counted in alphabetical order. I comes before M, so we're going to prefer to give the lowest locate number to the first substituent alphabetically, which is the isopropyl group. So we'll name this. Now, remember, you have to write your substituents in alphabetical order. So this would be named as 4 ethyl, 1 isopropyl, 2 methyl, cyclo, this is a 5-carbon chain, so this is pentane. For those wondering, why don't we give a locate number of 1 to the ethyl group? This would give a locate number set of 1, 3, 4, and 3 is greater than 2, so we do not give the ethyl group the locate number of 1. Remember, you start to assign substituents with the lowest locate number in substituent order. Then if there's a tie, then you start to consider alphabetical order in terms of assigning locate numbers. Okay, so let's talk a little bit about ring strain, torsional strain, and angle strain. So one thing that's unique about cycloalkanes is that cycloalkanes are less conformationally flexible. The ring does not allow perfectly free carbon-carbon bond rotation. If you look at cyclopropane, for example, if we wanted to rotate this front substituent and rotate our carbon-carbon bond 60 degrees, this would lead to an unrealistic and a bond angle that cannot occur. It would introduce way too much strain into the ring. So the carbon-carbon bond in cycloalkanes is more conformationally restricted, as rotating the carbon-carbon bond too heavily would end up breaking the ring open. Compared to a typical straight chain alkane, we can freely rotate the carbon-carbon bond. Cycloalkanes have generally less flexibility, as rotation of the carbon-carbon bond to a large degree would end up breaking the ring carbon-carbon bonds open. So because cycloalkanes are more conformationally rigid, at least in terms of carbon-carbon bond rotation, there are some additional considerations that we have to take into account when we talk about cycloalkanes. One of the major considerations that influences cycloalkane energy and one of the main sources of strain when we look at cycloalkanes is this idea of angle strain, which is the strain caused by distorting an sp3 carbon-carbon bond outside the normal 109.5 degree bond angle. If you think about a tetrahedral carbon, your bond angle is going to be about 109.5 degrees, and distorting beyond these normal bond angles will weaken your carbon-carbon bond. When you start to distort a bond angle beyond the typical carbon-carbon bond angle, that starts to put strain on the carbon-carbon bond and weakens the carbon-carbon bond because you're in part weakening some of the orbital overlap that makes up that bond. For example, cyclopropane has a huge amount of angle strain, as do cyclobutane ring systems. We're looking at massively distorted bond angles compared to the ideal tetrahedral bond angle. One thing I'd like to note is that rings larger than 3 atoms are not flat. Cyclic molecules can assume non-planar conformations to minimize angle strain and torsional strain by what's known as ring puckering. So for example, cyclopropane, it's stuck, but we can already see having these substituents eclipsed is very bad. So instead of having all the substituents eclipsed and instead of suffering these extreme distorted bond angles, your larger ring systems will pucker and adopt these distorted conformations to minimize angle strain and torsional strain. And we'll talk more about that. On the note of torsional strain is the strain caused by eclipsing and gauche interactions between ring substituents. Classic example of this is in cyclopropane. There are these very unfavorable eclipsing interactions between substituents. By the same token, if we look at larger ring systems, we may observe gauche interactions between axial substituents. This is called a Gauche methyl interaction, also known as a 1,3 diaxial interaction. We'll be talking more about these interactions momentarily. Let's look at some case studies of different cycloalkanes and talk about sources of ring strain and torsional strain. Cyclopropane. Cyclopropane is a cyclic 3-carbon ring. Cyclopropane has a lot of problems. Cyclopropane is planar with a highly distorted 60-degree bond angle. So this carbon-carbon bond angle is 60 degrees, which is highly distorted from the ideal bond angle for an sp3 carbon. Cyclopropane also has significant torsional strain as the bonds are locked in an eclipsed conformation. And unlike in a straight chain alkane, you can't exactly bend or rotate your carbon-carbon bonds because the carbon-carbon bonds are locked into a ring. There's much less conformational flexibility. So cyclopropane rings are highly strained. When we look at cyclobutane, cyclobutane has less angle strain than cyclopropane, and cyclobutane, unfortunately, because we have another carbon in the ring and another set of hydrogens in the ring, cyclobutane has more torsional strain due to the larger number of eclipsed ring hydrogens. To alleviate this torsional strain, cyclobutane adopts a puckered conformation where it bends one of its carbons out of the plane of the page. Why does it do that? If we look at the hydrogens in this puckered conformation, the hydrogens are not quite eclipsed, so we get a weaker eclipsing interaction, which leads to a more stable conformation. I wouldn't say this conformation is especially stable. It's just not getting highly destabilized by these full-on eclipsing interactions between all of the hydrogen atoms in the ring. So by adopting this puckered conformation, you bend your hydrogens a little bit out of the fully eclipsed conformation, and as a result, you get a weaker eclipsing interaction and thus a generally more stable conformation. This comes at a cost. When one carbon is bent out of the plane of the page, this increases angle strain in exchange for decreasing torsional strain. Looking at cyclopentane is a 5-carbon ring system. Cyclopentane has less angled strain than cyclobutane. However, when we think about planar cyclopentane, you wouldn't expect to see angle strain in planar cyclopentane, but cyclopentane is not planar, in part because it would have very high torsional strain to have all these hydrogens eclipsed. These ecliptic interactions are very, very bad. They're highly destabilizing. So rather than placing all of the hydrogens eclipsed in the planar cyclopentane conformation, cyclopentane adopts what's known as an envelope conformation to minimize torsional strain. Because, as we can see if we look down one of the carbon-carbon bonds, these hydrogen atoms are not fully eclipsed. So a common theme for cycloalkanes is they'll adopt these distorted geometries so that the carbon-hydrogen bonds are no longer fully eclipsed. So we exchange and we trade a little bit more angle strain for a lot less torsional strain. Let's talk now about cyclohexane, which is one of the more famous cycloalkanes, and it's going to be the topic of a lot of discussion in this chapter. Cyclohexane adopts a chair conformation with negligible torsional strain and no angle strain. Part of the reason why cyclohexane exhibits such low torsional and angle strain stems from the fact that if we look and we compare our substituents are staggered. In the chair conformation, all of the carbon-hydrogen bonds are staggered, so torsional strain is negligible. This is why cyclohexane adopts this quote-unquote chair conformation shown here. It ensures that there are minimal eclipsing interactions because all of your substituents are staggered. Now, how do we draw a chair conformation? Let's talk about some how-to guides because you're going to have to really be used to drawing chair conformations throughout this chapter. So one method is to draw 2 parallel lines. In this case, you'll want to make sure these 2 lines are slightly offset, and you want to make sure that the angle is not too heavily sloped. From here, you're going to place the topmost carbon atom above and to the right, and then place the bottommost carbon below and to the left. You're going to want to make sure that your carbon-carbon bonds are drawn parallel. So these 2 bonds are parallel to one another, as are these 2 bonds in the ring. So to put this all together, we would draw out our first set of parallel lines, then we'd connect them, then we'd connect them once again. You may notice that the method that I prefer to use to draw chair conformations is a little bit different than the method outlined here. This is another common method in which you start by drawing one line at a 60-degree angle. You connect to that a pair of lines, making a minor little curve at about a 15-degree angle. Then you draw a second parallel line, and then you connect and draw in the remaining 2 parallel lines. To show you what this looks like in practice, I draw my first line, I connect it with a pair of lines at a 15-degree angle. I draw my second parallel line, then I connect it with a second set of parallel lines, keeping in mind that we have 2 bonds in the ring that are drawn parallel, 2 bonds in the ring that are drawn parallel, and the 2 outer bonds in the ring are drawn parallel. This is going to take some practice, so I'd encourage you to practice drawing chair conformations until you're comfortable drawing both chair conformations quickly and efficiently. Whatever method you prefer, it's more than fine. Talking about cyclohexane chair conformations, we have to talk about the two types of substituents, which are axial and equatorial substituents. In chair conformations, substituents can be in what are known as the axial or equatorial positions. There are 6 axial hydrogens, which are drawn perpendicular to the ring. So these hydrogens in red are the axial hydrogens, while the 6 equatorial hydrogens are parallel to the ring. So these hydrogens in blue are the equatorial hydrogens. Shown here we have the equatorial hydrogen, and here in red we have the axial hydrogens. Now, it's really important to be able to identify axial and equatorial substituents, as the placement of substituents both has an influence on their reactivity in chemical reactions, and it has an influence on the given conformation's total amount of strain. So, how do we draw axial and equatorial substituents? So axial substituents alternate between pointing up or pointing down on adjacent carbons. There are 6 axial bonds, 1 on each carbon. The axial bonds are parallel and alternate between axial up and axial down. To make sure that we're comfortable with this, let's look at the other chair conformation. Let me draw this cyclohexane a little bit nicer. Okay, now let's add in our axial substituents. So we draw them pointing vertically, and we alternate between axial up and axial down. Thinking about it from the dash wedge perspective, the axial substituents alternate between being in the dashed and wedged stereochemistry, where the wedge substituents are pointing up and the dash substituents are pointing down. Importantly, axial substituents are drawn parallel to the ring, or the axial substituents are drawn parallel to one another. So all of these axial substituents are vertical, either pointing up or down. When we think about the equatorial substituents, let's talk now about the equatorial substituents. For the equatorial bonds, we have 6 equatorial bonds, 1 on each carbon, and these equatorial bonds are drawn parallel to the ring carbon-carbon bonds present. So for example, if we look at this carbon-carbon bond in the ring, we have a set of equatorial bonds that are drawn parallel to those ring carbon-carbon bonds. Notice the second set of equatorial substituents. We have 2 ring bonds, and the equatorial hydrogens are drawn parallel to those ring bonds. The last set of equatorial hydrogens are parallel to the last set of in-ring bonds. So, putting this all together, let's take these blank chair conformation templates and fill in the axial and equatorial substituents. The axial substituents are vertical, the equatorial substituents are parallel with the ring bonds. So for example, this ring bond corresponds and is parallel to this equatorial substituent. this ring bond here is parallel to this set of equatorial substituents. This ring bond is parallel to this equatorial substituent. And with that, we still have one last set of hydrogens. These two rings bonds are parallel to these two equatorial substituents. These last two substituents are often the easiest to misdraw, so it's important to make sure that your equatorial substituent bonds are parallel to the in-ring bond. See how these two lines are parallel to our two equatorial substituent bonds? It's very important. Take a moment and fill in the axial and equatorial substituents post chair flip, and then we'll discuss momentarily. So in this case, we're going to draw out the axial substituents. So we have 1, 2, 3, 4, 5, 6 axial substituents. Next, we're going to draw the equatorial substituents. Equatorial substituents are drawn parallel to the carbon-carbon bonds. So we have this equatorial substituent, shown here, and this equatorial substituent shown here. The next set of parallel bonds gives us two more equatorial substituents. The last set of parallel bonds gives us our last two equatorial substituents. One way to check that you've drawn your axial and equatorial substituents correctly is that it should look like a tetrahedral carbon, and the bond angle should look like about 109.5 degrees. Usually you'll be able to tell if you drew a substituent incorrectly, such as if you drew an equatorial substituent like so, because you'd notice that the bond angle would be distorted from the typical tetrahedral bond angle. I like using the parallel line check, but that's just my preference. Okay, so let's talk a little bit about conformations of cyclohexane and the ring flip. Cyclohexane doesn't exist in a single conformation. At ambient temperatures, cyclohexane converts between chair conformations via a ring flip or chair flip. In a chair flip, the axial substituents become equatorial and the equatorial substituents become axial. The two chair conformations interconvert rapidly and one may be favored at equilibrium. Generally, the lowest energy chair conformation is favored at equilibrium. So just to demonstrate what's happening here, this methyl group, which is in the axial position in carbon 1 is brought down, carbon 4 is brought up, and as we see, the methyl group went from being axial, it's now equatorial. One thing I'd like you to note, we went from axial up to equatorial up. So the overall stereochemistry and the overall configuration of this carbon center has not changed. This is an important idea that we'll touch on later. The other thing I'd like to draw your attention to is the fact that this hydrogen, which is in the equatorial position on carbon 4, ended up on the axial position on carbon 4. So let's talk about drawing both cyclohexane conformations. To draw a chair flip, I like to label my carbons 1, 2, 3, 4. We take our upmost carbon and we'll move carbon 1 down, and carbon 4, which is the bottommost carbon, will move up. Carbon 1 ends up as the new bottommost carbon. Carbon 4 ends up the new topmost carbon. All axial substituents become equatorial, and the equatorial substituents become axial. So for example, this substituent in the axial position is now in the equatorial position after the chair flip. This substituent in the equatorial position is now in the axial position post-chair flip. So let's continue on now, and let's talk a little bit about drawing different chair conformations, and let's practice and apply what we've seen. So here we're asked to draw the other chair conformation after a ring flip for each compound. I'll do the first example, you'll do the second. So in this case, we have an alcohol. This alcohol is axial at carbon 1. I'm going to label my carbons 1, 2, 3, 4, 5, 6. At carbon 3, we have an iodine, which is axial. And at carbon 4, we have a bromine that's equatorial. We're going to bring carbon 1 down. Carbon 4 gets brought up. So at carbon 1, the hydroxyl group is now going from axial to the equatorial position. So we draw the hydroxyl group at the equatorial position. Carbon 2 is just has hydrogens. Carbon 3, the axial iodine ends up equatorial. Notice hydroxyl group is pointing up, still pointing up. Iodine pointing up, still pointing up. Bromine in the equatorial position moves to the axial position. Notice the bromine was pointing up in the equatorial position. It's still pointing up in the axial position. We're then going to fill in the remaining hydrogens. And with that, we've completed our chair flip depiction. Let's now take a moment. I'd like you to draw the other chair conformation after a ring flip for the following compound. So pause the video, work through this example, and we'll discuss momentarily. Okay, so first and foremost, let's number our carbons. 1, 2, 3, 4, 5, 6. Carbon 1 gets brought up, so it ends up at position 1 as the topmost carbon. Carbon 4 gets brought down, which ends up at position 4 as the bottommost carbon. Adding in our carbon labels, 1, 2, 3, 4, 5, 6. At carbon 1, we have an equatorial ethyl group, which ends up axial. At carbon 2, we have an axial chlorine, which ends up equatorial. Carbon 3 just has hydrogens. Carbon 4 just has hydrogens. Carbon 5, we have an equatorial bromine, so the bromine ends up in the axial position. So with that, we've completed our chair flip. Okay, let's look at another example and let's talk a little bit about the ring flip. So in terms of the conformations of cyclohexane, the way that we interconvert between the two chair conformations is via a ring flip. And the ring flip goes through 5 unique conformations of cyclohexane. When you start to add substituents, you start to observe more unique conformations with differences in energy. For now, we're going to talk about the major conformations. The chair is the lowest energy conformation. Substituents are staggered with minimal torsional strain. Now, when you move one of your carbons up, so 1, 2, 3, 4, the first step in a ring flip is you move one of the carbons up or down. Moving carbon 4 up gives the half chair. Now, the half chair is the highest energy conformation due to eclipsing interactions. It's about 44 kilojoules per mole higher in energy, which is about 10 kcal per mole higher in energy. Next, continuing on, carbon 4 is brought further up, and this yields what's known as the twist boat conformation, which is shown here. The twist boat conformation is preferred over the boat conformation because it minimizes steric interactions. By adopting this twist boat conformation, we keep these two hydrogens from bumping into each other, and we minimize what's known as a flagpole interaction. So this is what the twist boat conformation looks like. Now, the key conformation that stands as the middle point is the boat conformation. To access the boat conformation, in essence, for the twist boat, one of the carbons is brought down, the second carbon is brought up. I would encourage you to try to walk through these different conformations with a model kit and physically try with a model kit to perform the chair flip. We'll have a supplementary video discussing that as well, where we do some work with a model kit. Now, the boat conformation is higher in energy than the twist boat due to these flagpole interactions, which are these steric interactions between these flagpole substituents. This introduces steric strain. From the boat conformation, you can access either of the chair conformations. In this case, since we brought carbon 4 up, if you bring carbon 1 down, you in turn will access the second twist boat conformation, the second half chair conformation, and finally continuing to bring carbon 1 down gets you to the second chair conformation. So in essence, in a ring flip, you bring one of the carbons up, up, and then the second carbon you bring down, down. Now, why are we talking about these intermediate conformations? Well, it's important to understand how a chair flip actually occurs and what intermediate conformations we're going through to get to the next chair conformation. And because for some odd cases, some of these less common higher energy conformations may be the most stable conformation in very niche cases. This energy diagram gets a lot more complicated for substituted cyclohexane rings, as each chair, half chair, and twist boat conformation has a different energy. Now, let's discuss cyclohexane and cycloalkane stereochemistry, and let's start by discussing this in the context of monosubstituted cyclohexanes. As cycloalkanes do not have free carbon-carbon bond rotation, substituents on each ring face are unique. A wedge bond indicates that the bond is pointing up and out of the plane of the page. So this wedge indicates this bromine atom is pointing up. What that means is that if we have our plane of the page, this bromine atom is always going to be pointing up, be it axial up or equatorial up. The key thing is that dash wedge does not indicate whether a substituent is axial or equatorial. It just indicates whether the substituent is pointing up out of the plane of the page or down into the plane of the page. So wedge bonds are pointing up. As a comparison, dashed bonds are pointing down below the plane of the page. For example, this alcohol has a dashed bond, which tells us it's pointing down. This can be equatorial down, or it could be axial down. In either case, as you can see, the dashed bond is pointing down, while the wedged bond is always pointing up. So let's practice this And I'd like you to try to draw the chair conformation for the following molecule, and I'd like you to draw a dash wedge structure given the following chair conformation. So pause the video, work through these examples, and then we'll discuss momentarily. Okay, so looking at this molecule, we have a wedge bond, which tells you that this sulfur group is pointing up. I'm going to arbitrarily label this as carbon 1. You can really put this group at any carbon number because we just have one substituent. You just need to make sure that its stereochemistry is consistent. Okay, this thiol group is pointing up. So at carbon 1, the up position is axial. After a chair flip, we move this carbon 1 down, carbon 4 up. That in turn gives us a sulfur group in the equatorial position, but still pointing up. Okay, perfect. Now let's talk about going the other direction, taking a chair conformation and drawing a dash wedge structure. So this chlorine is equatorial, and as we see, this bond is pointing down, while the hydrogen bond, carbon-hydrogen bond, is pointing up. So what that tells us is, at this carbon, the hydrogen has a wedge, the chlorine has a dash. That tells us that this chlorine is pointing down. So again, dash wedge does not tell you whether a substituent is axial or equatorial, just whether it's pointing up or pointing down, above the plane of the page or below the plane of the page. Okay, let's talk a little bit about cycloalkane stereochemistry in the context of cis and trans stereoisomers. Stereoisomers are structures with the same connectivity, same formula, but a different 3D shape. An example of this are cis and trans stereoisomers, where we have the same connectivity, but as you can see from these three-dimensional pictures, these two molecules have dramatically different 3D shapes. Does everyone see here how the chlorine is in a different position if we compare these two chair conformations, and thus how these two molecules have a different shape? These two structures represent stereoisomers, specifically cis-trans stereoisomers. So what are cis and trans stereoisomers? The cis stereoisomer occurs when the substituents are on the same face of the ring, either both up or both down. In this case, if we have the bromine and chlorine both with a wedge, these substituents are cis. So in this case, we have the bromine equatorial, the chlorine axial, both pointing up. In the second case, post chair flip, the bromine is axial, the chlorine is equatorial, both of these substituents are up. One thing that I'd like you to keep in mind here is that the carbon numbering has remained consistent pre and post chair flip. When you start to have multiple substituents, you want to make sure that you keep the substituents on their original carbon. You don't start moving substituents around. For those who are paying attention and being a little bit observant to this definition, we've drawn just one of the cis stereoisomers. The other cis stereoisomer possible for this molecule has both the bromine and chlorine pointing down. This is the other cis stereoisomer. We'll talk about the relationship between these two cis stereoisomers in a moment. As a preview, this is the enantiomer of this compound. The trans stereoisomer occurs when the substituents are on opposite faces. In this case, the bromine has a wedge, the chlorine has a dash. The bromine is pointing up in the equatorial position. The chlorine is pointing down in the equatorial position. Post chair flip, we have the bromine pointing up in the axial position and the chlorine pointing down in the axial position. Now, this specific relative arrangement of substituents is known as a trans-diaxial relationship, where the bromine and chlorine substituents are both in the axial position and they're trans to one another. This term will come up later on when we discuss certain reaction mechanisms, such as elimination reactions. Okay, so let's apply what we've learned and let's identify the following compounds as the cis or trans stereoisomer. So pause the video, take a few moments to work on these examples, and then we'll discuss. So taking a look here, we have an alcohol with a wedge, a chlorine with a dash. These two substituents are trans to one another. The alcohol is pointing up, chlorine's pointing down. In this next case, we see the bromine is pointing up, the alcohol is pointing up. The dash wedge equivalent of this would be 1, 2, 3, 4. We have the bromine with a wedge, 1, 2, 3, 4. The alcohol also with a wedge. So this would be the cis stereoisomer. These two substituents are both pointing up. They're both on the same face. These two substituents are cis to one another. Wonderful. Let's keep going now and let's talk a little bit about drawing chair conformations for polysubstituted cyclohexane rings. Cyclohexane has two faces with substituents either pointing up or down. Now, any substituent pointing up above the plane of the ring are given a wedge. Any substituent pointing down are given a dash. This is not directly related to axial and equatorial. Substituents in the axial position alternate between up and down on each carbon. As you can see, we have a hydrogen pointing up in the axial position, and then a hydrogen pointing down in the axial position. By the same token, substituents in the equatorial position alternate between down dash and up wedge. As you can see on carbon 1, if the axial substituent is pointing up, the equatorial substituent is pointing down. By the same token on carbon 2, if the axial substituent is pointing down, the equatorial substituent is pointing up. So, in summary, each carbon has a dash and wedge substituent. The axial and equatorial substituents alternate between dash and wedge as we move around the ring. So, each carbon has one axial and equatorial substituent, a dash and wedge substituent respectively. Wedge and dash substituents alternate between axial and equatorial positions on each carbon. So what can we do with this observation? Well, there are a few things that we can do. We can use this observation to draw polysubstituted cyclohexane rings. So the approach I like to take is you label a carbon with a substituent as carbon 1. You label the other carbons counting clockwise. Next, if the substituent has a wedge, on carbon 1, draw it pointing up. Place it axial or equatorial so it points up. If it has a dash, draw it pointing down, and you place that substituent axial or equatorial so it points down. Repeat for all substituents. I know some people like to memorize this mnemonic of alternating axial and equatorial. I find it's easier just to think in terms of whether the substituent is pointing up or down. So for example, in this case, we labeled our carbons 1, 2, 3, 4, counting clockwise. We label our ring 1, 2, 3, 4. As you can see, the bromine has a wedge, so we draw the bromine pointing up. Moving to the next carbon, we see that the chlorine has a dash, so we need to draw it pointing down. On carbon 2, the position pointing down is the axial position. Looking at carbon 4, the methyl group again has a wedge, which tells us it's pointing up. The up position on carbon 4 is in the equatorial position. The reason why I like this dash wedge method is it allows you to draw chair flips very quickly. So if we draw this molecule post chair flip, 1, 2, 3, 4, 5, 6, carbon 1 gets brought down, carbon 4 gets brought up. In this case, carbon 1, we have a bromine. The bromine must be pointing up. The up position at carbon 1 is the equatorial position. At carbon 2, the chlorine has a dash. The position that's pointing down would be the equatorial position. Carbon 4, the methyl group, has a wedge, so it's pointing up. So the position pointing up at carbon 4 is the axial position. So we draw our methyl group. Again, you check your substituents. You check whether they're dash or wedge. Wedge substituents get drawn pointing up. Dash substituents get drawn pointing down. Let's now try to apply what we've learned, and I'd like you to draw the chair conformation for the following molecule, and I pre-labeled one of the carbons as carbon 1. So take some time, pause the video, and then we'll work through this example. Okay, so first things first, I'm going to label my carbons counting clockwise. Next, I'm going to look at my first carbon. At carbon 1, we have the fluorine, which has a dash, which means it's pointing down. At carbon 1, the position that's pointing down is the equatorial position. The hydrogen is pointing up. Carbon 2, nothing of interest. Carbon 3, we have the methyl group with a wedge, which means it's pointing up. That would be the axial up position. From here, carbon 6 is the next carbon of interest. The alcohol has a wedge, so it's pointing up. The up position in this case would be the equatorial position. If you're ever unsure, draw out the hydrogen, as that can let you check your work. As you can see, if we translated this correctly, the hydrogen, the alcohol, and the methyl group have a wedge. So just to check, Hydrogen, alcohol, methyl group wedge, all of these groups are pointing up. The fluorine has a dash, so it's pointing down. Post chair flip, we bring carbon 1 down, carbon 4 up. From here, the fluorine is still pointing down. The down position in this case is going to be axial. The methyl group at carbon 3 is still pointing up. That position will be equatorial this time. Carbon 6, the alcohol is still pointing up. So the up position is axial in this case. Just to make sure that we've done everything properly, hydrogen, methyl, alcohol still all pointing up, so we're good to go. Also, as an additional check, we notice that after a chair flip, all of the axial substituents end up equatorial, all of the equatorial substituents ended up axial. Okay. Now, why do we care so much about being able to draw substituted cyclohexane rings? Well, we need to be able to draw these ring systems in order to analyze them via conformational analysis. So what is conformational analysis? Well, to start this discussion, let's look at a monosubstituted cyclohexane ring, and let's look at the energy and the relative amount of steric and torsional strain found in each conformation for a monosubstituted cyclohexane ring. So as we discussed, cyclohexane ring flips rapidly between chair conformations at room temperature. The two conformations of monosubstituted cyclohexane in equilibrium are not equally stable, and thus the more stable conformation is favored at equilibrium. What we can note for a monosubstituted cyclohexane ring is that if we compare the equatorial conformation to the axial conformation, the equatorial conformation is lower in energy. And the reason for that is the equatorial conformation lacks these interactions that we call 1,3 diaxial interactions. These interactions are destabilizing, and this leads to an energy difference between the two conformations. Thus, at equilibrium, the more stable equatorial conformation is favored. Now, in terms of how favored, as a general rule, based on the energy difference in kilojoules per mole, that determines the relative percent at equilibrium. When you start to get above about 5 kilojoules per mole in energy difference, you'll start to see one of the conformations to be pretty much the predominant conformation at equilibrium. Now, what are these 1,3 diaxial interactions that we've discussed? The equatorial conformation is generally lower in energy, and that's because the axial conformation is higher in energy due to steric strain caused by 1,3 diaxial interactions, where a 1,3 diaxial interaction is a steric interaction between a substituent and axial hydrogen atoms. So in this case, we have two methyl hydrogen 1,3 diaxial interactions. And this is about 2 times 3.8 kilojoules per mole, or about 7.6 kilojoules per mole of steric strain. This methyl group in the axial position bumps into these other axial hydrogens, and this creates steric strain. For those who notice, this particular number is suspiciously similar to a number that we used in prior chapters. That's not a coincidence. 1,3-diaxial interactions are steric interactions between axial substituents, and another name for a 1,3-diaxial interaction is a Gauche methyl interaction. Now, how do we quantify diaxial strain? We use what are known as A values, which is the steric strain value for the 1,3-diaxial interaction between a substituent and a hydrogen atom. So in this case, if we have a methyl group axial, we have 1, 2 methyl hydrogen 1,3-diaxial interactions for a total of 7.6 kilojoules per mole of strain. Given this A value table, I'd like you to tell me what's the total amount of diaxial strain that's present if we have this alcohol in the axial position. Pause the video, take a few moments, and then we'll discuss. Okay, so in this case, we have 1, 2, so we have 2 alcohol hydrogen diaxial interactions, 1,3-diaxial interactions. So in this case, the alcohol A value is 2.1 kilojoules per mole times 2 interactions gives us 4.2 kilojoules per mole of strain. Okay, so let's unpack now the 1,3-diaxial interaction. And to do that, we're going to look at some cyclohexane Newman projections. We can generate a Newman projection for cyclohexane by looking down a given carbon-carbon bond. In this case, we're looking down the C1 to C2 bond and the C5 to C4 bond. In this case, instead of having 1 front carbon, we have 2 front carbons in our Newman projection. So here's what a model of this cyclohexane chair conformation looks like. I would encourage you to make this same model and look down the carbon 1, carbon 2 bond. Let me put some labels here. This is carbon 1, this is carbon 2, this is carbon 5, this is carbon 4. And carbon 6 is right here. As we can see, this bridging carbon 6 is pointing up. The bromine is pointing up and to the left. And this methyl group on carbon 1 is pointing down. So here's what the Newman projection looks like. In this case, we're just drawing what we see. As you can see, we have the hydrogen, hydrogen, the bromine, bromine, the back hydrogen, and hydrogen, the bridging methylene group. One moment. The bridging methylene group, which is pointing up. On carbon 1, we have the hydrogen and the methyl group. In the back carbon, we have 2 hydrogens, one pointing up, the other pointing down and to the right. And the back bridging methylene is pointing down. So we're able to construct a Newman projection from our model and from the chair conformation given. Post chair flip, again, we are still looking down the carbon 5 to carbon 4 bond and the carbon 1 to carbon 2 bond. So carbon 1 and 5 are still in front. Here's what the model looks like. Here's carbon 1. Carbon 2 is in the back. 3 is here. 4 is in the back. 5 is up front. And 6 is up front. As we notice, the bridging methylene group is now pointing down. The methyl group is now pointing down and to the right. The hydrogen is pointing up. The back hydrogen is pointing up and to the right and down. And the back bridging methylene is now pointing up. The bromine and hydrogen on the front carbons are pointing up and down and to the left, respectively. Notice in both cases, the bromine is pointing up and the methyl group is pointing down. Now, why do we draw these Newman projections? One, they can help us visualize certain interactions. And two, they're really useful to help us understand the true nature of a 1,3 diaxial interaction. So again, we can make these Newman projections by making a model of our molecule, making a model of our chair conformation, and looking down any set of carbon-carbon bonds. I just chose this particular set of carbon-carbon bonds for consistency. Now, let's do a case study and let's draw chair conformations for the following compound. And then let's draw Newman projections for each chair conformation, looking down the C1, C2 bond. And we're going to do this to answer the question, which conformation is lower in energy? So I'd like you to pause the video, take a few moments to fill in these chair conformation and Newman conformation templates, and then we'll discuss. Okay, so in this case, I'm going to label my carbons as one. I'm going to do it this way. 1, 2, 3, 4, 5, 6. There are many ways that we can number it. I'm just trying to think of the way that makes it easiest to see. Because we're looking down the carbon 1, carbon 2 bond, let's use this numbering convention. 1, 2, 3, 4, 5, 6. Okay, so carbon 1, we have this alcohol that has a actually, because we have this numbering convention already where we're numbering 1, 2 counterclockwise, let's just keep that consistent. Okay, so carbon 1, we have this methyl group. It's pointing up. The up position is the equatorial position. The alcohol is pointing down. That would be the equatorial position as well. Okay, let's add in the remaining hydrogen atoms. Okay, now looking down the carbon 1, carbon 2 bond, we see we have the methyl group in the front, the hydrogen in the front, and the alcohol and hydrogen in the back. For the rest, we just fill in the hydrogens. As we can see here, we have a methyl hydroxyl interaction, and this is an interaction that we've seen before. What do we call this interaction when we have two substituents separated by a 60-degree dihedral angle? This is a gauche interaction. And this costs about 2.1 kilojoules because our A value is about 2.1 kilojoules. Let's see if we see this kind of gauche interaction once again. Post chair flip, carbon 1 goes up, carbon 4 goes down. On carbon 1, we have our methyl group. Carbon 2, we have our alcohol. This time, because the alcohol starts pointing down, and carbon 2, our alcohol will continue to be pointing down. Notice the methyl group was equatorial, and now it's axial. The alcohol was equatorial, now it's axial. Filling in our hydrogens, we finish this chair conformation. So we see that we are already setting up for some unpleasant 1,3 diaxial interactions between the methyl group and the axial hydrogens and the hydroxyl group and the axial hydrogens. Let's take a look at the Newman projection. So we're looking down the C1 to C2 bond. Now, we can use this numbering. It's more than fine. However, given our perspective and given the fact that when we look down the C1, C2 bond, in this case, this should be number 3 and this will be number 6. So looking down the C1, C2 and C5, C4 bond, on carbon 1 we have our methyl group and a hydrogen. Carbon 2 we have a hydrogen and the hydroxyl group. Carbon 3 we have 2 hydrogens. Carbon 6 we have 2 hydrogens. Carbon 4 and 5 we have 2 hydrogens. And this really lets us see the true nature of the 1,3 diaxial interaction. The reason why the 1,3 diaxial interaction is called a gauche methyl interaction stems from the fact that in reality, it's not just the fact that this methyl group is bumping into these axial hydrogens. It can also be paralleled, and you can also think it very similar to if you had two substituents, in this case, two methyl groups, gauche to one another. A 1,3 diaxial interaction is really a gauche interaction between the axial substituent and a methylene group present in the ring. So the reason why 1,3 diaxial interactions and gauche methyl interactions have very similar energies is because they're the same interaction. So even though we can visualize 1,3 diaxial interactions like above, where we have this axial methyl group, these axial hydrogens, and they're bumping into each other, you can also visualize it from a Newman projection perspective, where we have these two substituents separated by a 60-degree dihedral angle that are gauche to one another. And because these substituents are gauche, they can bump into each other, and it's this steric interaction that's the real source of strain in 1,3 diaxial interactions. So this is the parallel between a 1,3 diaxial interaction and a gauche methyl interaction. They're the same thing. And the way that we can see that is by looking at Newman projections. So from this note, and to really drive this point home, let's calculate the total amount of strain in this right conformation. In this case, we have two OH methyl diaxial interactions, which is 2.1 times 2 kilojoules, and we have two methyl hydrogen diaxial interactions, which is 3.8 kilojoules times 2. In total, we have 7.6 plus 4.2, about 11.8 kilojoules. As we can see, 2.1 is far less than 11, so the conformation on the left is lower in energy. Note, whether you calculate these diaxial interactions as gauche methyl or 1,3 diaxial interactions, the strain values are the same because they're the same interaction. We can even see this right here, where a OH hydrogen diaxial interaction is the same as a methyl hydroxyl Gauche interaction. So this is why it's important to be able to draw Newman projections for cyclohexane rings, because they can help you see things that would otherwise be difficult to see and identify, such as the fact that there are Gauche interactions that can exist in cyclohexane ring systems, and we've discussed in detail the true nature of a 1,3 diaxial interaction. So, just to summarize this, a 1,3 diaxial interaction is identical to a Gauche methyl-methyl interaction. The axial group encounters steric strain with the methylene group attached to the adjacent carbon. So as we can see, here is a typical Gauche interaction. Here is a 1,3 diaxial interaction. And as you can see, they're the exact same interaction. The reason why this only occurs when the substituent is axial is because when the substituent is equatorial, we see that the equatorial substituent is anti to the ring methylene group. We can see that this dihedral angle is 180 degrees. There's no proximity between these two substituents. Again, this destabilizing Gauche interaction only occurs when the substituent is axial, and thus placing substituents axial is less favored. An axial substituent will experience two steric interactions with the two adjacent ring methylene groups. And that's why a 1,3 diaxial interaction has the same energy as two Gauche methyl interactions. One other thing that you need to consider in polysubstituted cyclohexane rings are Gauche interactions. If a ring has substituents on adjacent carbons, a Gauche interaction can occur. For example, in the following molecule, the chlorine is wedged up, methyl is dashed down. In one conformation, we have the chlorine in the equatorial up position, the methyl is equatorial down. As you can see, these two substituents are gauche to one another, and so we have a gauche methylchlorine interaction. As you can see in this model here, where we have the chlorine and the methyl group gauche to one another, and they're able to bump into each other in 3D space. Let's take what we've learned and let's take a look at the following molecule, and let's identify any Gauche interactions present, as well as any 1,3 diaxial interactions present. So, in this case, let's take a look. I'm going to label my carbons as follows. It's completely arbitrary. You can pick any carbon numbering method you want. I'm going to number it this way, counting counterclockwise, just to set up and make the Gauche interactions a little easier to see. Both of these substituents are wedged, so both of them are pointing up. So we have our ether group pointing up, the isopropyl group pointing up, and as we can see, we have a Gauche interaction between the isopropyl group and the ether group. To drive this point home, looking at the numbering convention shown here, at carbon 1, we have our ether group, carbon 2, we have the isopropyl group, and the ether group and the isopropyl group are bumping into each other. They are gauche to one another. Post ring flip, carbon 1 gets brought up, carbon 4 gets brought down. So in this case, the ether, which was equatorial, is now in the axial position. The isopropyl group is now placed in the equatorial position as it was originally axial. One thing that I do want to draw your attention to, this bond isn't drawn correctly. If we wanted to draw this accurately, we would draw it with this angle. Okay, looking at the Newman projection, looking down the carbon-1, carbon-2 bond, we have this ether pointing up axial, and the isopropyl is equatorial. One thing that's pretty interesting in this case is we can't escape the fact that in both conformations, we have an ether isopropyl group gauche interaction. This is very common if you have both the substituents cis and they're on adjacent carbons, they'll have a persistent gauche interaction in both conformations. Now, are these gauche interactions more destabilizing compared to a 1,3 diaxial interaction? No, they're considered on equal footing. So you always have to take into account both the gauche interactions and the 1,3 diaxial interactions when deciding what conformation is lowest in energy. Again, if you need additional assistance visualizing these gauche interactions, I would encourage you to make a model, just like we've done in this photo here. Okay, let's do some conformational analysis for polysubstituted cyclohexane ring systems. And let's do a case study involving 1,2-dimethyl cyclohexane. Our goals in this case are to identify the lowest energy conformation and identify the lowest energy molecule or isomer. As discussed, 1,2-dimethyl cyclohexane can exist as the cis or trans stereoisomer. And let's look at both. For cis 1,2-dimethyl cyclohexane, we have the following two possible chair conformations. Both cases, the methyl groups are pointing up. One of the methyl groups will be axial, the other methyl group will be equatorial. As a result, we have a methyl-methyl gauche interaction, and we have a 1,3 diaxial interaction between the methyl group and the axial hydrogens. In total, this gives 7.6 plus 3.8, which gives about 11.4 kilojoules per mole of total strain. Because we have the same interactions in both conformations are equal in energy. So for cis 1,2-dimethyl cyclohexane, both conformations are equal in energy. For trans 1,2-dimethyl cyclohexane, trans 1,2-dimethyl cyclohexane exists mainly in the diequatorial conformation. If you had to make a guess with no other information, generally the lower energy conformation will place the most and the largest substituents equatorial. Why is that? For trans 1,2-dimethyl cyclohexane, which would be this depiction, we have one methyl group up, the other methyl group down. One conformation has both methyl groups equatorial, the other conformation has both methyl groups axial. In the equatorial conformation, we have a gauche interaction between the two methyl groups. In the diaxial conformation, we have 1, 2, 3, 4 methyl hydrogen diaxial interactions. And as we can see, the diequatorial conformation is lower in energy. Even though we have a gauche interaction, it is lower in energy. And overall, this conformation is lower in energy in part because it doesn't have these highly destabilizing diaxial interactions. So you have to take into account both gauche interactions and diaxial interactions when identifying the lowest energy conformation. So the diequatorial conformation is the lowest energy conformation. Okay, let's keep going now. And let's do some examples now. The first type of case study we're going to do is we're going to work on problems where we're asked to identify the lowest energy conformation. So let's apply what we've learned in the prior examples, and I'd like you to draw both chair conformations for the following compound, and I'd like you to identify the lowest energy conformation, and I'd like you to calculate the steric and torsional strain for each conformation. So I'd like you to pause the video at this time, work through these examples, and then we'll discuss momentarily. Okay, so first things first, let's number our carbons. I'm going to use this arbitrary numbering. I'm going to draw out my chair conformation. From here, I'm going to number my chair. For carbon 1, the ethyl group has a wedge, so it's pointing up. The methyl group has a wedge, so it's pointing up. On carbon 2, the up position is in the equatorial position. Carbon 5, the chlorine is pointing with a dash, so it's pointing down. The down position on carbon 5 is the equatorial position. Next, I'm going to draw the chair flip. Carbon 1 is brought down, carbon 4 is brought up. Okay, carbon 1, the ethyl group, to be pointing up, is going to be in the equatorial position. Carbon 2, the methyl group, to be pointing up, will be in the axial position. Carbon 5, the chlorine, to be pointing down, will be in the axial position. I'm going to draw out all of the hydrogens now because it's going to be important for this analysis. Okay, now let's take a tally of all of the interactions. So in this case, first and foremost, we have an ethyl-methyl gauche interaction, which is about 4 kilojoules. Next, we have this ethyl group axial. So we have 1, 2 diaxial interactions. Which cost us 4 kilojoules, and we have 2 of them. So in total, we have 12 kilojoules per mole of strain. Looking at the chair flipped form, again, we have an ethyl-methyl gauche interaction. Which is 4 kilojoules. And then we have diaxial interactions between the methyl group that's axial and the 2 axial hydrogens, and the axial chlorine and the 2 hydrogens. So we have 2 methyl hydrogen diaxial interactions, which cost us 3.8 times 2 kilojoules. And we have 2 chlorine hydrogen diaxial interactions. This has an A value of 1, so this costs us 1 times 2 kilojoules. So in adding it up, we have 6 plus 7.6. It gives us 13.6 kilojoules of total strain. So as we can see, the conformation on the left is the lowest energy. No, these conformations are pretty close in energy, but a 1.5 to 2 kilojoule per mole energy difference does mean this conformation on the left is going to be much more predominant at equilibrium. So, as a general rule, the lowest energy conformation will place the largest and most groups equatorial. So then, let's try to apply what we've learned now, and I'd like you to draw both chair conformations for the following compounds, and I'd like you to identify the lowest energy conformation. This time, you only have to do a calculation if you feel it's needed to justify your assignment. So, pause the video, take a few moments to work on this example, and then we'll discuss. Okay, so first and foremost, I'm going to number my carbons. I'm going to draw out a chair. From here, I'm going to number my carbons. For carbon 1, this tert-butyl group is pointing up, so it's axial. This is already setting off some alarm bells. This tert-butyl group is huge. It's pointing up, and having this large group in the axial position is highly destabilizing. A tert-butyl group has an A value somewhere around 13 to 14, so you don't want to place this group axial. Carbon 2 has a methyl group, which is pointing up, which means it's in the equatorial position. Let me draw this a little more pronounced. Carbon 3 has a methyl group, which is pointing down because it's dashed. Now, without doing any calculations, this tert-butyl group, we're not going to place that axial. That's way too much strain. This tert-butyl group just bumps into everything. This tert-butyl group is huge, and you don't want to place these large, bulky groups axial if you can help it. So let's look at the chair-flipped conformation. So in this case, carbon 1 gets brought down, carbon 4 gets brought up. So now we have the tert-butyl group equatorial, much better. The methyl group, let me keep the numbering consistent. 1, 2, 3, 4, 5, 6. For carbon 2, the methyl group is pointing up. That position will be axial. Carbon 3, the methyl group is pointing down. So instead of being equatorial, it's now axial. Okay. So in this case, we have a choice between two hydrogen tert-butyl interactions, which is about 14 times 2, or 28 kilojoules of 1,3-diaxial strain, or 4 methyl hydrogen interactions, which is about 4 times 4, or 16 kilojoules per mole of strain. As we can see, the conformation that places this giant tert-butyl group in the equatorial position is going to be lowest in energy. In most cases, when you have a very large group like a tert-butyl group, I'd say as a rule of thumb, the tert-butyl group is almost always going to be equatorial. because placing a large group like a tert-butyl group axial, it just introduces too much strain. Okay. Let's look at another case study where this time we're asked to identify the lowest energy compound given a pair of compounds. So in this case, we're asked to draw both chair conformations for the following compounds, calculate the total strain, and circle the lowest energy conformation for each compound, and circle the lowest energy compound. So I'd like you to pause the video, take a few moments to work through this example, and then we'll discuss. Okay, so first and foremost, let's do some carbon numbering. 1, 2, 3, 4, 1, 2, 3, 4. I'm going to draw out one of my chair conformations. In this case, both the methyl group and the tert-butyl group are pointing up. In this case, at carbon 1, the up position is axial. The 4 position, the up position is equatorial. Without doing any calculation, this is going to be the lowest energy conformation for this compound because it's the only one that places the tert-butyl group in the equatorial position. Post chair flip. 1, 2, 3, 4, 5, 6. Carbon 1, the methyl group is now equatorial. And carbon 4, the tert-butyl group is now axial. This first structure has some 1,3 diaxial interactions, which I will draw out. In this case, the structure on the left has 2 methyl hydrogen diaxial interactions, which cost us about 3.8 times 2, or 7.6 kilojoules of total strain. The structure on the right has 2 tert-butyl hydrogen diaxial interactions, which costs us around 14 times 2, or 28 kilojoules of strain. Let's look at structure number 2 now. Filling in our chair conformations. One, 2, 3, 4. Carbon 1, the methyl group is still pointing up. Carbon 2 has hydrogens. Carbon 3, the tert-butyl group, if it's pointing up, it's axial. And this is pretty bad because we have, in this case, not just 1,3 diaxial interactions between a group and hydrogen, we also have the tert-butyl and methyl group. So we have a tert-butyl methyl diaxial interaction. We have a tert-butyl hydrogen diaxial interaction, and we have a methyl hydrogen. So we have about 13 kilojoules. This is just estimating, I'd say around 17 kilojoules, and the methyl hydrogen is 3.8 kilojoules. So in total, this is about 33.8 kilojoules of total strain. Let's look at what happens post-chair flip, as we may get some relief from all of this strain. Carbon 1 gets brought down, carbon 4 gets brought up. 1, 2, 3, 4, 5, 6. In this case, the methyl group is equatorial. And the tert-butyl group is also equatorial. So in this case, in the following conformation, There is no strain due to steric and torsional interactions. As a result, this conformation is the lowest energy conformation. Comparing these two lowest energy conformations, we have 7.6 kilojoules per mole of strain versus no strain. So this molecule here would be the lowest energy. Now, this was the quantitative approach. The qualitative approach is just simply if we compare the lowest energy conformations. In this structure, the methyl group is axial. In this conformation, the methyl group is equatorial. So this lowest energy conformation of the lowest energy molecule places the most substituents equatorial and minimizes 1,3-diaxial strain. Okay, let's take a look at one last type of problem. In this case, we're asked to identify the lowest energy stereoisomer. So you're going to draw both chair conformations of the following compounds and calculate the total strain. You're going to circle the lowest energy conformation for each compound and circle the lowest energy compound. So I'd like you to take a few moments to work through this example, and then we'll discuss momentarily. So you may want to pause the video at this time to give you some time to work through this problem. Okay, so I'm going to number my carbons, and I'm going to draw out my first chair conformation. The methyl group is pointing up because it has a wedge. The chlorine is pointing down because it has a dash. The down position on carbon 3 is equatorial. Post chair flip, let me redraw this. Okay, post chair flip, the methyl group on carbon 1 gets brought down, carbon 4 gets brought up. The methyl group is now in the equatorial position. The chlorine is now in the axial position, still pointing down. Okay, let's now add in the relevant hydrogens. Okay, now let's take a tally of our diaxial interactions. In this case, we have two methyl hydrogen 1,3-diaxial interactions, which cost us 3.8 kilojoules times 2, or 7.6 kilojoules. Looking at this structure and this other conformation, we have two chlorine hydrogen 1,3-diaxial interactions, which cost us about 1.0 kilojoules times 2, or 2 kilojoules of total strain. So here we have our lowest energy conformation. Now, without doing any calculations, I'm going to tell you that these two molecules have the same energy. The reason why I know this is that these two molecules are enantiomers of one another. And as we'll see in the next chapter, enantiomers have often identical properties. We're going to prove this more rigorously. So let's look at the two chair conformations for our second compound. So first and foremost, in this case, the methyl group has a dash, so it's pointing down. This time the down position is equatorial on carbon 1. For carbon 3, the chlorine has a wedge, so it's pointing up, so it is axial. Now, as we can see, and I would encourage you to make a model to see this, these two structures are mirror images. These two conformations are mirror images of one another. And so what that means, and one of the implications of that, is that they have the same interactions. We can show this. Here we have two chlorine hydrogen, 1,3 diaxial interactions, which cost us 2 times 1.0 kilojoules, or 2 kilojoules of total strain. Looking at the post-chair flip compound, post-chair flip conformation, we bring carbon 1 down, carbon 4 gets brought up. The methyl group is now axial. The chlorine is now equatorial. As we can see, we have 1, 2 methyl hydrogen diaxial interactions, which gives us 2 times 3.8 kilojoules, or 7.6 kilojoules of total strain. So as we can see, this structure and this conformation on the left is the lowest energy conformation, and these two molecules have identical energies, which makes sense because they're enantiomers. Okay, so we've done a variety of examples involving conformational analysis. Let's talk now about another factor that can influence the energy of different conformations. So hydrogen bonds and hydrogen bonding. Hydrogen bonds are strong stabilizing interactions. They provide about 20 kilojoules per mole of stabilization. Alcohols, amines, carboxylic acids, and amides are capable of forming hydrogen bonds. Structures capable of intermolecular hydrogen bonds will place hydrogen bonding groups gauche or diaxial if necessary. So for example, in this case, if we have a 1-2 relationship between these alcohols, we're going to prefer to place these two hydroxyl groups gauche, in part to allow these two groups to hydrogen bond. Now, because a hydrogen bond is so stabilizing, structures capable of intramolecular hydrogen bonds will in fact prefer to place hydrogen bonding groups diaxial. So in this case, even though This diaxial conformation suffers a minor penalty because you have 1,3 diaxial interactions. That penalty is made up by the fact that this hydrogen bond is very stabilizing. It's about 20 kilojoules per mole in terms of stabilization. So you can think of it as adding negative 20 kilojoules per mole to your total for energy calculations. So anytime you have groups that are capable of an intramolecular hydrogen bond, you're going to place those groups either gauche to one another if they're on adjacent carbons, or diaxial if they're 1,3 to one another. This allows the two groups to hydrogen bond. Importantly, the groups must be in close proximity, and they must be in close proximity in order for this hydrogen bond to occur. You're not, for example, if we look at the following conformation, we're not going to want to place this amine and alcohol diaxial in this case because how will they hydrogen bond? The answer, they won't. So you want to make sure your hydrogen bonding substituents are 1,3 diaxial and they're close in proximity in 3D space. This enables them to hydrogen bond and enables the molecule to be stabilized by this hydrogen bonding interaction. Okay, so let's apply what we've learned, and I'd like you to draw the lowest energy conformation for the following molecule. So I'd like you to take a few moments, pause the video, and work through this example. Okay, so looking at the relationship, we have 1,3 relationships between these hydrogen bonding substituents. So let's try to place all of these substituents axial and see what happens. So if this is carbon 1, the axial position on carbon 1 will be pointing up. At carbon 3, the axial position points up. At carbon 5, the axial position points up. As you can see, when all of these hydroxyl groups are axial, they're capable of hydrogen bonding, and this will be the lowest energy conformation because we have multiple hydrogen bonds occurring. This conformation is far more stable than the alternative tri-equatorial conformation, where in this case, the alcohols are not in close enough proximity to hydrogen bond. So let's now talk a little bit about fused ring systems. So fused ring systems, or polycyclic ring systems, are compounds with two or more rings connected at adjacent carbon atoms. An example of this is Decalin. Decalin has two stereoisomers, cis and trans Decalin, where trans Decalin has these hydrogens trans to one another, while cis Decalin has the two hydrogens cis to one another. Looking at cis and trans Decalin in a little more detail, in cis Decalin, the bridgehead hydrogens are cis. In trans Decalin, the bridgehead hydrogens are trans. Importantly, trans Decalin is lower in energy as the hydrogens and ring atoms are equatorial. So do you see the ring carbon bonds? They're in the equatorial position. Comparatively, cis-Decalin places the ring substituent axial and has an additional gauche interaction. So in this case, if we look at cis-Decalin, this ring substituent is axial, and as such, there's a gauche interaction between ring substituents. Looking at a model, we can even see this gauche interaction across this carbon-carbon bond. where we have the Gauche interaction between these two substituents. Now, the cis and trans Decalin rings also have some differences in terms of ring flip capability. Cis Decalin can ring flip, trans Decalin cannot, as it would give an impossible bond angle. This does not happening. This is not happening. So cis Decalin is capable of a ring flip, trans Decalin is not. I would encourage you to make a model and try doing the ring flip for cis Decalin and attempting the ring flip for trans Decalin. Be careful when you attempt the ring flip for trans Decalin. Don't strain your model kit too hard because it will break as this bond becomes increasingly distorted. Now, why am I talking about these fused ring systems? Well, these fused ring systems have a unique shape. As you notice, cis Decalin almost looks like a cupped hand. And as a result, reactions will interact with each face of the Decalin ring system differently. And this allows you to run reactions with stereoselectivity. So this is the first example, and these fused ring systems are often key examples in what's known as facial selectivity. And this is a tool that chemists can use when they're designing a synthesis in order to prepare molecules with stereoselectivity and stereo control. Now, we've talked a lot about fused compounds. There's another class of polycyclic or bicyclic compounds, which are known as bridged compounds. Bridged compounds are compounds with two or more rings sharing two or more atoms. For example, bicyclo-2,2,1 heptane, bicyclo-2,2,2 octane, and bicyclo-3,3,1 nonane. These names may look intimidating at first, but the method for naming these bridged compounds is actually quite intuitive. So the first thing you're going to do is count the total number of carbons to determine the root name. For example, this is a 10 carbon ring, so it's going to use so for 10 carbons in this case, we're going to use the 10 carbon prefix, which, as we'll see later, is decane. Likewise, this ring system, depicted in these two ways, has 6 carbons. So we'll use the hexane name base. Now, we're then going to number our carbons, and we're going to count starting at the bridgehead of the largest ring, and we're going to number the longest path between bridgehead atoms. So in this case, here's the first bridgehead. I'm going to do 1, 2, 3, 4. And I'm going to count and specifically note the number of carbons in between the two bridgeheads. So this is 1, 2 carbons. Next, I'm going to count between my bridgehead once again for the next longest path. So in this case, I'm going to count this 1 carbon bridge. Finally, I'm going to count the shortest path, which is another 1 carbon bridge. Looking at this larger molecule example, if we count the longest path, this gives us 1, 2, 3, 4, 5, 6, which in turn would be 1, 2, 3, 4 carbons. The next longest path is 1, 2, 3 carbons wide. And the shortest path let me use a different color for that. And the shortest path is 1 carbon wide. So now that we have the path lengths for each of these structures, what you're going to do one moment, is you're going to count the number of carbons in each path and arrange the numbers in descending order. In this case, we have lengths of 4 carbon, 3 carbon, and 1 carbon. So we'd arrange this as 4, 3, 1. Going back to the second example that we've been looking at, we've established that we have a 2 carbon, 1 carbon, and 1 carbon chain between our 2 bridgeheads. So we'd write this as 2, 1, 1. To write the full name for our compound, you're going to name the compound starting with the prefix bicyclo, then the numbers, then the chain name. So this compound on the left would be bicyclo 431 decane. Likewise, this compound on the right would be bicyclo 211, and because this is a 6-carbon ring system, this would be named as hexane. Remember, this is the total number of carbons in this bicyclic structure. The last thing I want to draw your attention to is a bonus appendix, which discusses common mistakes that I often see when students draw cyclohexane chair conformations. Let's talk about these common errors and the issue with each of them. So first, the substituent position doesn't change during the ring flip. So if, for example, you have this methyl group at carbon 1, post ring flip, carbon 1 is right here. So as you notice, this methyl group has moved and you've moved it to another carbon. The reason why this is not a proper chair flip is this is just the same molecule rotated. You have a methyl group in the axial up position, and you have a methyl group in the axial up position. These are the same thing. This error also can be worse if you have other substituents, because if you move substituents across carbons, you could potentially end up drawing a constitutional isomer. So what this is drawn is essentially something like this. And you haven't really drawn the other possible chair conformation. The second error is the substituent position doesn't change during the ring flip. So for example, you have carbon 1 here, carbon 1 moves down, and carbon 1's here, but your substituent is still drawn on the same carbon. What you've done essentially is you've moved your substituent 1 carbon over. So even though you went from an axial to an equatorial substituent, what you've done is you've changed from an axial up to an equatorial down substituent. This is very bad. What you've essentially drawn is a methyl group with a wedge on the left and a methyl group with a dash on the right. These are stereoisomers, and these are not identical molecules. So please just be careful of that. The last thing I want to highlight is an issue that arises when you have cis and trans stereoisomers, which is the question, what specific stereoisomer? There are usually at least 2 possible cis and trans stereoisomers. For example, cis 1-ethyl 3-methyl cyclohexane can represent either of these 2 molecules, which both have the cis arrangement. Cis and trans is ambiguous. For example, trans 1-methyl 2-propyl cyclohexane. Take a few moments and try to draw the 2 possible structures that would match that name. So in this case, trans 1-methyl 2-propyl. So if we have a methyl group and a propyl group, to have them trans, the methyl will be pointing up. The propyl group will be pointing down. The other possible structure that matches this trans arrangement of substituents would have the methyl pointing down and the propyl group pointing up. Cis and trans is ambiguous. And to resolve this ambiguity, we're going to use a more precise naming method that we'll talk about in future chapters. As a preview for the next chapter lecture series, these two possible structures that we've drawn for each cis and trans stereoisomer are a pair of compounds known as enantiomers, which are non-superimposable mirror images. We will talk a lot more about enantiomers in the next chapter lecture series. So this concludes the Chapter 4 lecture series, and we'll be continuing on the Chem 12 Organic Chemistry lecture series with a discussion of Chapter 5.